Have you ever really wondered how an engineer learns their craft? I mean, the actual step-by-step journey from a totally blank page to a working device? Well, today, we're going to be analog architects. We're going to pull apart a real university electronics course to build a blueprint for how this amazing technology is actually made. So, let's dive right in.
It's a fair question, right? We live in this digital world. It's all about clean code, powerful processors, ones and zeros. So why would anyone focus on what seems like the old school world of analog circuits? In an age of pure data, why does this physical, tangible tech still matter so much? Well, it's because the real world doesn't speak in ones and zeros, not at all. It speaks in waves, temperatures, pressures, and sounds. All of these are continuous analog signals. Analog circuits are the absolute, indispensable link between our physical world and the digital one. They are the bedrock of everything from the smartphone in your pocket to the most advanced medical devices out there. So, here's our game plan for today. We'll start with why analog is still king. Then, we'll meet the basic building blocks, the transistors. We're going to uncover the ultimate multi-tool, the op-amp, and see how to literally make circuits come alive. We'll bridge theory with practice, and finally, we'll look at the complete toolkit an engineer walks away with. Okay, so let's start with that core idea. Why does analog still rule? Simple. It's because it isn't just a prerequisite, it's the very foundation. Every single digital system, I don't care how complex it is, relies on a well-designed analog circuit just to function. It really is the unsung hero of all modern tech. So, how do you start building? Well, you start with the absolute fundamentals. Think of these as the first tools you're ever given. Before you can build a house, you need to know how to use the bricks and bolts. In electronics, that means mastering the transistor. The journey kicks off with the bipolar junction transistor, or BJT for short. This is the original workhorse. And students don't just learn what it is, they learn how to tame it. They have to master things like biasing to set it up just right, stability to keep it running reliably, and modeling so they can predict exactly how it's going to behave in a circuit. This is where precision engineering really begins. Now, once the BJT is in the toolkit, it's time for an upgrade. This is kind of like going from a trusty hand drill to a super high-powered electric one. Students get introduced to field effect transistors, or FETs. They're more modern, way more efficient, and they just open up a completely new world of design possibilities. And this, right here, just illustrates the learning process so perfectly. It's a totally logical progression. You start with the basics, the BJT. Then you build on that with the more advanced transistors. Then you get the powerhouse tool, the op-amp. And finally, you get to use all of them to start creating real things like oscillators. Okay, now for my favorite part. If transistors are the individual tools, then the operational amplifier, or op-amp, is the fully loaded Swiss Army knife. It's this incredibly powerful and versatile little chip that can be configured to do almost anything you can imagine. And this list really shows you why it's such a game changer. An op-amp isn't just one thing. Students learn how to wire it up to do, well, almost anything. Perform math, filter out unwanted noise, compare signals, and even convert those real-world analog inputs into the ones and zeros our computers understand. It's amazing. So with this powerful toolkit in hand, it's time to get creative. This is the part of the course where students go from just analyzing circuits to actually designing circuits that generate signals, keep time, and perform active functions. This is where the real magic happens. The next step is learning how to make a circuit that creates its own signal. That's an oscillator. And students learn the fundamental rules, like something called Barkhausen's criteria, which are basically the two key conditions a circuit has to meet to start and sustain a signal. It's like the recipe for creating an electronic heartbeat. And here is where it gets so cool. This is a direct quote from one of the actual course assignments. Students are tasked with designing oscillators that produce specific musical notes. I mean, come on. This isn't just abstract theory. It's a tangible, creative, and super memorable way to apply these complex ideas. This is how you make engineering sing, literally. Of course, a blueprint is totally useless if you can't actually build the house. So the next critical step in an engineer's journey is bridging that huge gap between the formulas on the page and a real functioning circuit on the workbench. And this is exactly how it's done. The course explicitly connects every major theoretical concept to a hands-on lab. You learn about amplifiers in a lecture, then you go right into the lab and you build one. You study filter theory, then you design and test a real filter. You learn about oscillators, then you build what's called a Wien-Bridge oscillator and see it work with your own eyes. And it doesn't stop with the physical hardware. Modern engineering is also about virtual design. Students have to master industry-standard software like Multisim and LabVIEW. They learn to build and test their circuits in a simulation before ever touching a real component. This is how modern products get developed, and it's an absolutely critical skill in that final toolkit. So after weeks and weeks of lectures, labs, and simulations, what does that final complete toolkit actually look like? And more importantly, how do we know the engineer has truly mastered it? Here it is. A graduate of this course doesn't just know things, they can do things. They can analyze and design with any major type of transistor. They can wield that op-amp like a master craftsman. They can create signals out of thin air with oscillators and timers. And crucially, they are fluent in both the physical lab and the virtual simulation world. And you know that mastery is rigorously tested. It's not just about one big final exam at the end. The evaluation is really balanced. A huge chunk of it, almost a quarter, comes from the continuous, hands-on work in labs and assignments. The rest is split between major exams, making sure they're assessing both the theory and the practical skills. And this number represents the weight of that whole journey. 4.5 credits. That signifies a substantial, really demanding course that forms a major pillar in an electronics engineering education. It's a testament to just how deep and broad that toolkit really is. So we've gone from the simplest brick, that little transistor, all the way to designing and simulating complex functional systems. The student has been totally transformed into an analog architect, armed with a complete toolkit of skills, ready to build the technology of tomorrow. And that leaves us with one final thought. The power of this toolkit isn't just in analyzing what already exists, but in creating what comes next. So, if these tools were in your hands right now, what's the first thing you would build?